So I am Joseph, and I'm a PhD student at Delft University of Technology, which is based in the Netherlands. And this is work from me and my colleagues Moritz, Konstantinos, and Georgios. And it's about the promise and perils of adopting static analysis in dependency analyzers. So I think, yeah, most of you are well aware of that. There are lots of like dependency tools coming up these days, and lots of also interesting plugins that you can install if you're a package manager. And yeah, I mean, for example, we have like Snike, Eclipse Ready, Cargo Bloat, Cargo Denied, etc. But there's also a growing problem with using all of this tooling, and I'm usually like always reading one or the other thing on Twitter, and there's always like this kind of things. People start commenting that you just created their like simple React app, and it finds that there are 96 vulnerabilities. Or that, hey, when I was running npm audit, it says I have vulnerability, panic, blah blah blah, and I think there was one really great like blog post by Dan Abramo called npm audit broken by design. And I think in this blog, what I really liked was that he basically mentioned what I like the problem with having this kind of false positives, saying that there are like 75 vulnerabilities, but it's really unclear how those really affect your own application. And that was the reason why I sort of created this talk, because I was like doing research into looking into basically like doing regular metadata-level analysis versus doing call graph analysis. And as a solution to this sort of false positives, I'm seeing a lot of tools moving towards the direction of using static analysis. I think there are two prominent projects. I haven't, let's say, like looked very clearly, let's say, like from a very broad perspective, but two that I'm aware of is basically Snike and also the Eclipse study. And there's also like the Fasten project, which is like an EU project that I'm working at the university, where we're trying to do call graph analysis at the scope of a package ecosystem / repository. To basically understand what I'm talking about when it comes to metadata-based, let's say, like analysis or analyzer versus like static analysis. So we have like the project, and when you resolve, you get like your direct dependencies, and they usually are versioned as well. And then you also, of course, have like the transitive dependencies as well. And in general, like the representation is that you have a dependency tree, which basically represent build dependencies between packages in your project. And the usual analysis is that you do some kind of reachability analysis. So for example, version 1.02 might be vulnerable. And by doing reachability analysis, we can say, this is a package that you use and that particular version, so it is vulnerable. What is like really nice with this approach, which is also like the most adopted one, is that it's like super fast and very easy to do. And but the main problem is that you don't do any code analysis. You're basically using build metadata to like try to infer how your project is basically using other libraries. Then there is the so-called more program analysis-based dependency analyzers, and the one that I'm showing is basically like a call graph analysis. So you have like your own project, you're calling certain functions, and then through those functions you're using, let's say, like other functions in in dependencies that you have imported, and you also, of course, have like transitive dependencies. And here, for example, like if you compare to the previous approach, we might have the function called, let's say, like unused in this package. And we see that in the call graph, this function is not used at all. So if that function will be vulnerable, we can be very clear, say like, well, this is not really used by the project, etc. So like, yeah, usually the representation is basically a call graph, and usually at the scope of a program and its dependencies. And then the analysis, of course, is reachability analysis. And through call graph, you basically somehow get like a usage-based analysis. As I was saying with the unused example, is that you kind of know what are the things that you are using from your libraries that you have imported. The pro, of course, is that it's like fine-grained and has precise analysis. The con, on the other hand, is that the accuracy varies. And that is, for example, in relation to using like a dynamic language like Python or JavaScript. Or also, like in general, you might have projects that heavily use code generation, etc., and like call graph generators might not be able to capture those function calls. And of course, by moving the scope to the dependencies, it becomes more expensive to compute. If you use more like accurate algorithms, that also becomes very expensive. And from my experience, like building call graphs of many projects, it can also quickly become very large and maybe not the most easiest to sort of try to understand and digest sometimes. So like if you think in an ideal world, we would of course like have a very strong preference to use static analysis. However, as I was mentioning, that dynamic analysis languages, it could be a problem. It's not easy to construct call graphs from that. And then the other thing is that package repositories are not a homogeneous collection of software or like packages, because usually, like if you look in static analysis, and I also see that in many static analysis paper, we usually like pick very nice projects to analyze that fits our, let's say, like analysis perfectly. But in reality, packages like use very different language features, and the accuracy depending on which package you analyze might really vary, and that's not very easy to, let's say, like see or understand. And in many cases, it might be that, for example, precision is maybe not the most important case. For example, in the case of maybe automated dependency updating, if, for example, you use static analysis and there is like a false positive, and through that false positive, you're, let's say, like avoiding an update, then the library maintainer will think, it's not like a major issue. So I think it really varies depending on the use case that you have. And of course, clearly, like a lot of trade-offs to be made in general. And I think as a, let's say, like developer or project teams that work in developer tools, the kind of question you might ask is like, should I really sort of go towards adopting static analysis in general? So then the question is like, what are actually really the trade-offs if we go a little bit more in depth into it? I think something wrong in the animation here. Sorry. And what I did is like I conducted a large study of the Crates IO repository. So I did this back in early 2020. So I basically took 140K releases, which is from almost 24K packages. Sorry, the reverse. I had 208 releases, 100K releases, and from 35 packages, and I was able to generate 142K call graphs and 200K from 200K packages. And I was just like very curious if I do a very simple analysis, like counting the number of dependencies per package in this data set. So what I want to know is like, okay, I use the metadata analysis, how many dependencies are you using versus using the call graph in general. And I think from there we can like a little bit understand what are like differences. So here I say don't bother so much about the figure in general. But what we can see here, for example, like when we look at the median number of dependencies, so these are like 3 different networks. So Crates.io is basically like the metadata network. Docs.rs I basically like looked at dependencies that we're actually able to build, and then Prezi is basically like the call graph analysis. And overall, when we look at the median, but also like the mean as well, we can see that all those 3 approaches are very comparable when it comes to number of dependencies. And that basically shows that, well, maybe for like when you're analyzing, let's say, like direct dependencies, there might not be like a major gain by using static analysis, for example. When we go to transitive dependencies, the situation is much more different. So here I find that when I compare these 3 different approaches, like they actually do not, I mean, apart from the Docs.rs and Crates.io, like they're relatively comparable. But when I compare with the call graph based approach, the gap is quite wide between, let's say, like the median. So the median, for example, in Feb 2020 is 17 dependencies, let's say transitive dependency, whereas in the case of the call graph, it's 6 of them. Then the question is like, who is actually right and who is more close to reality? And I basically did like a manual inspection. And basically it classified what are like the reasons for 34 dependency relationships. And I mean, trying to, let's say, like understand all dependencies. I mean, like analyzing projects is of course very difficult, and you definitely get a big headache when you try to look into other projects that you don't really know. But the main prominent reason, for example, why we see that there's an over approximation in metadata-based networks, or like in case if you would analyze, let's say, like counting number of dependencies, is that most of them are actually not reachable in general. And then it's like question, okay, why are they not, let's say, like used at all? And I think this really comes down that when we do this metadata-based analysis, we make an assumption that I think not many always think, but the assumption is that we expect that a project uses all APIs of its direct dependencies, and then it uses all APIs of its transitive dependencies, which does not really match with reality. And if you see this example, like looking at the transitive dependencies, so for example, here we see that foo uses bar, and bar then uses used, and then intern. But here we have, for example, like unused, and unused doesn't use like lib version 3 in this case over here. So here, if we use, let's say, like the call-based approach, we know that, okay, app basically use lib 1 and lib 2, but not really lib 3. Whereas if we would do the metadata-based approach, it would consider all of them used. So it basically really shows that context has a very, very big importance. Let's see. Oh, yeah. And then, of course, there are cases where the call graph-based analysis was not really great, and that was really in relation to like data type information and usage. I basically didn't take into account like implementation of traits, etc. But I think that should somehow be able to handle with some better additional analysis. And also, like it was not able to capture C function calls properly. So what is sort of like my main sort of recommendation based on the results I'm seeing is that so I would really give the case for metadata if you only look at the direct dependencies. And I think in a way it also sort of makes sense a bit. Like if you have a library, you cannot try to use, I mean, not like all of its APIs, but I think a large number. And I think also the other part is that there are huge cost benefits, like you save, let's say, like the trouble of constructing call graphs. Also, projects that, let's say, like rely heavily on code generation dynamic techniques. So I think in the case, I didn't really have this issue in Rust because, whenever you use macros, like you will see the macro calls, in the final binaries or in the last stage of the compilation. And the other thing could also be the case of soundness. If that is like super crucial, there might, for example, be you might have a, let's say, like a dependency, and you have, for example, like some kind of dynamic invocation or something that the call graph generator is not able to capture. If you miss relationships to that dependency, that could be like very critical, and then using call static analysis is not a good idea. What is like the case for static analysis? I think really when it comes to doing like a whole dependency tree analysis or analysis that generally involves transitive dependencies, it really shows that context is very crucial because we don't use all the APIs of our direct dependencies, and that also has implications of what transitive dependencies we use. I remember one case like in a Rust library, I can't remember exactly which one it is, but for example, you might have, for example, like this conditional compilation or additional flags. If you don't, for example, use like a regex component in your direct dependency, then you won't really be using the transitive dependencies related to the regex, let's say, like functionality, for example, like the regex library, etc., that comes with it. So it really has a big impact. And I think the other really major benefit is that you have better actionability, because if you can pinpoint where exactly in the code it is, it's also much more easier to like debug around it. And in cases where precision is, for example, more important than soundness, I think it's a good case in general. But I think also, important thing to keep in mind is also like it's, of course, much more difficult to do this for dynamic languages like Python or JavaScript. So if you want to know more about this, let's say like work in general, like I have on archive, this is actually was accepted for a journal recently. So it's called Prezi from package-based to call-based dependency networks. It's quite a large journal in general, but yeah, some of the things I discussed here is like extracted from this paper. So I'm happy to take questions related to this.
Thanks, Joseph. One more very interesting talk from you. Um, I have a question. Do you think bubbling up metadata from transitive dependencies would help with the static analyzers capturing accurate data?
So you mean with respect to doing like the typical metadata-based analysis, like if we had more, let's say, like context information, or
Yeah.
I think that could potentially help. I think it's actually a very good question. I think the other problem is that when we look at these transitive dependencies, we're really interested in what kind of behavior are you actually using from these transitive dependencies, because function calls basically tells us what are like the execution flow to these libraries, and I think without having that information inferred. So in the case of static, let's say like statically dispatched function calls is relatively straightforward. But when it comes to dynamically dispatched, that might be a bit more trickier. But I think
Okay.
definitely like as a, let's say like maybe middle ground, like this could be a good way to basically bubble up more information. Because I think the important part is that we need to try to adopt more code-centric analysis and not solely rely on simply metadata.
Okay, let me check the chat to see if there's more questions. Um, okay, I think I have another question for you. So you did say that soundness is more important than precision. Can you explain more about what you meant by that?
So in the case of, so I think the most prominent case is security. So you would really like to, let's say, like avoid a scenario where you have, let's say, like through precise analysis, and for example, you're not able to handle one language feature very properly. So if you're not able to handle that language feature properly, then it could be possible that there might be some vulnerabilities that you're not able to see directly. And that in like some companies or in some cases is like a really a no-go. So it's better to have more false positives just to be, let's say, like on the safe side. But I think in general this is like always like a very debatable thing. I think also like in academia they sometimes focus a bit too much on soundness and not, for example, on like having more practical solution. So yeah, so that is like my sort of relation to soundness. Although I think I'm generally like more somewhere in the middle. I think it should be to some degree sound, but also like to some degree precise, because having too many false positives is also not very helpful and productive in general.